Now, let's see, now why does gamma go to 0? So gamma, where's gamma? Gamma here. Okay, can you see this? I should have spelled it out a bit more. V naught A is delta, right? V naught A is delta, and delta is finite, right? It's less than infinity. Delta is finite. So you've got a V naught A here, that's a delta, but you've got another A as well. So you've got like delta A here. Now A is going to 0, and V naught A, that's finite. These are all finite, but you've still got an A term in here which goes to nothing, and therefore gamma goes to nothing, right? So as A goes to nothing, your gamma goes to nothing from here, right? Now as your gamma goes to nothing, have a look at this formula. Now as gamma goes to 0, what's your n? What's the value of your n? Well, as that goes to nothing, and it's got to be larger than something, so that something's got to be nothing, right? So effectively, n here has to be 1. Okay, so as gamma goes to 0, n has to be 1. And what's n? N is the number of bound states, the number of eigenstates, the number of wave functions stuck or bound within your well, right? So as in other words, if you have a delta well, it'll only have one wave function, one bound state. It will be the ground state. That's all there is. There's only one, right? And it comes as a consequence of this inequality. So I'll just say it again. As gamma goes to 0, this n has to be 1. Right? If you have a look at that, you'll see that's the case. All right. So in the limit, your delta well will, here it is, it's almost closed and almost infinitely tall, but it'll look like this pretty much in the limit. Now that's the well. So what about the wave functions that exist within this well? Well, they will have the following form. In this region, in regions 1 and 3, you had an exponentially decaying, here and here, exponentially decaying wave function. So they're dropping down exponentially of that form. Now the width here is virtually 0, so there's no cosine term in here. It's effectively squashed to nothing, right? So all you're left with just the two, like the wings, two exponential forms, right? Okay, now we start doing. So we've got the wave function. We've got the u now for a delta well, right? The u will look like this. These two forms, but this one sort of gets squashed out of existence. But from continuity conditions, the conditions you impose on the wave function we've been doing, we do have the following. This b here, when x goes to 0, as your a gets really small, so your x goes to 0, so this is effectively 1, so you just left with b. As x goes to 0, this is also 1, and you've got continuity, therefore b and c have to be equal. Follow that? Just from continuity. So we know b equals c. So whatever this is, these c's here, will have the same value as this, right? Okay, now we start doing some a whole string of deductions. Where we're now trying to find the E, right? So we've got the waveforms, but what about the eigenvalue, the energy, the allowed energy? What is this one allowed energy? We only allowed 1 from here. Okay, as gamma goes to nothing, n has to be 1. So we do have 1 ground state, bound state energy, but what is it? So all this balloon, all this algebra here is just to derive a formula for the energy. It's way down here after a lot of algebra. So let's just plow through it now. Okay. Right. Now we're assuming the energy is less than the depth of the well, so E is less than V naught. Okay. Now this, what is this? This is alpha, isn't it? By definition. Yeah. Okay. So this expression for alpha, that will be less than this expression. Now all I've done, I've just changed, instead of E here, I've put V naught. Right? Now we've assumed that E is less than V naught. So therefore this here will be less than that. Right? Why? Well, because V naught is larger than E. Right? So, so we've got that. But what is this? That's alpha by definition here. Right? This is just alpha. So alpha is less than that. So alpha is less than this expression here. Here written is here. Okay, so now multiply both sides by A. You may be asking at this stage, why? What's the point? It's a stepping stone. In fact, it's a stepping stone to a stepping stone. In fact, it's a stepping stone to a stepping stone to a stepping stone. So, yeah, with the benefit of hindsight, you'll see the point. All right, just as long as you follow it. Okay, so alpha is less than that expression. So multiply both sides by A, and so alpha A will be less than A times this. Okay, now take the A inside, so you'll square it inside the square root. Okay, so here's the A squared inside the square root, and I've not written it as A squared. I've written it as just AA. Why? Because I can take this product now of V naught A. Now that V naught A is delta, right? Here, right? V naught A is delta. So I can just, for V naught A here, I can just put a delta there. Okay. Now, now as A, the width of your well, as A goes to 0, this expression here goes to 0. Why is that? Well, M, H, delta, they're all finite, right? Delta by definition is finite. But A is going to 0. Therefore, this whole thing goes to 0 as A goes to 0. Right? So as A goes to 0, this whole square root thing also goes to 0. Right? Because of the A. Okay, so now this thing here is larger than alpha A, right? It's larger than alpha A. But this thing's going to 0 as A goes to 0. Therefore, this alpha A must go to 0. Okay? Alpha A must go to 0 as A goes to 0. Now, alright, keep that on the back burner for a while. We'll use it later. But it's a stepping stone to a stepping stone. Right. Now we're talking about the well, the square well, and for the case of even parity. Now go back to an earlier session. You remember this for the square well case, that the tangent for even parity, tan of alpha A equals beta over alpha. We derived that earlier. So if you're a bit rusty, go back and study that. Right? So we have this expression. Now look, alpha A is going to 0. It's getting really small. Right? As the width, your A, as the width of your well gets smaller and smaller, A gets smaller, and alpha A goes to nothing. Now we've got a tangent of alpha A here. So this alpha A is getting really small. Okay. So as alpha A gets really small, tangent of alpha A you can approximate as just roughly alpha A. Tangent of a small quantity, very small quantity, is roughly equal to the small quantity. So tan, for a small x, tan x is roughly equal to x. Right? So tan alpha A is roughly equal to alpha A. Okay? Now, alpha A is roughly equal to beta over alpha. Where'd that come from? Where did that come from? Where did that? Oh, here. Okay, it came from here. Okay, now alpha A is small, right? So tan of alpha A is roughly alpha A. So here, instead of writing this, tan of alpha A, you just